So once again, welcome to a new problem. This time we're given a shelf. It's a wood shelf, and it happens to have a groove like that. And so the uh, the groove is holding the shelf, and it goes all the way up until inside. So you can assume this is um, like a wall holding it. The thickness of the shelf happens to be given as 3 centimeters, and also the entire length of the shelf from the wall up until the right edge is given as 32 centimeter, and then also the depth of the shelf going into the wall is equivalent to 2.0 centimeters. So this is the information that's given. It's fastened inside the slot. So this is a slot that holds the shelf. You can think of it like a slot like that holds the shelf. The first thing you want to do is, well, on top of that, we're given that the mass of the shelf is equivalent to 6.6 kilograms. We want to find the, we need a free body diagram. That's the first thing we need. Off the shelf, assuming that you're going to have two vertical forces at this point. This is a special point where the groove is, where the slot is. The second thing about the problem is that we need to find the size of all the forces. So the size of all the forces involved in the problem, in keeping equilibrium. That's one thing we want to do. And also the next thing we want to deal with is we want to find the torque due to the slot supports. Remember, the shelf is being supported by slots. Well, it's a single slot, so we want to see what's the torque. So the first thing we'll do is go ahead and have a free body diagram. There's a groove like that, and there's a wall, a shelf popping out from the groove all the way up until the right side, and we do have the weight in the middle of the shelf acting downwards, mg. This distance is still 32 centimeters, doesn't change. Just like the distance that the shelf moves into the slot is given as 2 centimeters. There is a force acting downwards that's supposed to balance out the shelf. So, first of all, this force is pushing upwards. So there's a force pushing upwards right here on the right of the slot. So I'm going to call that Fr. And then there's another force pushing downwards to balance out that force, and I'm going to call it FL for the left force. That's your free body diagram. The other thing that happens is the right force, this one right here, Fr, is responsible for the torque that balances out the weight. Okay, so that's what Fr is responsible for. The second part, the other thing we know is that FL has no torque, but gives equilibrium to FR. Okay, it has no torque, but gives equilibrium to FR. If we're gonna take the torque around this point right here, if we're going to take the torque around this point right here, that's what's going to happen. FL is not going to have a torque, but then we'll have a clockwise torque due to mg going that way, and that's a negative torque. And then we're going to have a counterclockwise torque due to fr, and that one is going that way, so that's going to be a positive torque. Those are the pieces of information that we're dealing with at this point. The sum of forces in this system in the y direction is 0, and then also the sum of torques is also going to be 0. So since the sum of torques is 0, we take the force to the right and multiply that by 2 centimeters. It's a positive torque, and then the weight is going to give a negative torque. So if you go back, you see that the distance from this point up until the end of the slot is equivalent to 32 centimeters plus 2 centimeters. But then the weight acts in the middle, so it splits this distance in the middle, so that has to be divided by 2, and that gives us 17 centimeters. Going back, the perpendicular distance of the weight is 17 centimeters, and since the system is in equilibrium, we make all of that equals to 0. Our purpose is to solve for this right force. So then we have FR being equivalent to mg, 17 centimeters over 2 centimeters. So FR becomes equals to the mass, which is 6.6 kilograms, times the acceleration due to gravity, which is 9.81 meters per second squared. And then we do have these units canceling out. 17 over 2, that's equivalent to 8.5. It's just a unit, so nothing changes. So the force we're getting due to the reaction on the right becomes equivalent to 549.8 newtons. That's the force we're dealing with on the right. And then the next thing, we need to find the torque provided by the right force. But prior to that, we can also find the left force. Remember, all the forces involved include the left one and the right one. We found the right one, and then we want to find the torque responsible produced by the right force. So going back, we see that the sum of forces in the y direction is 0. The sum of forces in the y is 0. So if you assume upwards is positive and downwards is negative, you can see that this is going to be positive. The left force will be positive, the right one will be negative, and the weight will be negative. So this means that F left minus F right minus mg. Well, actually, we need to change that a little bit. The left force is pointing downwards, so it's not negative, but it's going to be positive. This one right here is negative. The right one is positive because it's pointing upwards, and then the weight is also negative because it's pointing downwards. So we have to change the signs for all of these to make our life easier in solving the problem. So we'll start with the right force because it's pointing upwards, and therefore you're going to have FR. And also that's positive. FL is negative because it's pointing downwards, and the weight is negative, it's pointing downwards. Our goal is to solve for the left force. So FL becomes, if this one moves to the right, it becomes positive. So we have FR minus mg. In the previous page, we were able to solve for FR, which is 549.8 newtons. We want to subtract the weight, which is 6.6 kilograms times 9.81 meters per second squared. And so if you simplify that, you get the left force being equivalent to 485.1 newtons approximately. Those are the two forces involved. Part of the problem was to solve for the size of the forces. So we used, in the first page, we used the torques around this edge right here. Okay, so we had a positive torque coming off of the right force, and we also had a negative torque coming off of the weight, the right torque and the weight, and we're able to isolate the right force and solve the problem for 549.8, and then we again use the sum of forces in the y to solve for the left force. And finally in the problem, we have to determine the torque as a result of the right force pointing upwards. So the sum of torques about our famous edge, this is our edge right here, the sum of those torques is 0. And we are only interested in the torque provided by FR. FR, as you can see, is pointing upwards, so the torque due to FR is counterclockwise, so it's going to be positive torque. So then we say T is FR times 2 centimeters, which is FR, remember, was given us 549.8 newtons. Multiply that by 2 centimeters, but you have to change that to meters, so you use unit conversion, and so our torque becomes equivalent to approximately 11 meter newtons. Hope you enjoy the problem. So this is the torque exerted by the support, this support right here, the right support, it's the main one. That's the torque being exerted, so we're looking for this torque. So hope you enjoy the problem. Feel free to send any questions or comments, and have a wonderful day. Okay, thanks, bye.